Hello everyone, I'm Shivani Kumar, and today in this poster for RISE, I'm going to present my ECL 2022 publication discussing sarcasm explanation in multimodal multi-party dialogues. While a lot of work has been done in the domain of sarcasm identification in standalone as well as conversational text, a very few work, close to none, has been done in explaining the sarcasm in it. To bridge this gap, we propose this new task of sarcasm explanation in dialogues. Since the task is new, we propose a new dataset for it. We call the dataset WITS, short for Why is this sarcastic? The dataset contains multimodal code-mixed conversation transcribed from a TV series called Sarabhai vs. Sarabhai. Now that we have our dataset and the problem definition ready, we move on to the methodology. Before any deep learning architecture, it is important to get a representation for the inputs. So in order to get the acoustic representation, we use the OpenSmile Python library and get a representation for each of the audio input that we have. To get the visual representation, we use the ResNext 101 model that is trained on kinetics dataset and obtain a representation for each of the video input that we have. For the text part, we use any text-based backbone like BART or MBART to get a representation of those texts. Further, in order to fuse the three modalities together, we take inspiration from the already existing context-aware attention. Now, context-aware attention says that in order to get the actual essence of the whole input, we must include the context explicitly in our key and value vectors of the whole attention mechanism. So they use this first equation to get the modified key and value vectors that have the context information explicitly in them. This lambda parameter is used to control the extent of the context information that we want in the modified vectors. We take the same concept and apply it to capture the multimodal aspect of our inputs. For our work, this context vector becomes the multimodal vector. So in order to get the acoustic context-aware self-attention vector, we use the acoustic representation that we obtain from OpenSmile library as the context vector, and then use the same equation that the authors of the original paper provide to get the multimodal information condition key and value vectors. Once we have those vectors, we perform the traditional scaled dot product attention over them and get our final representation for acoustic infused and visual infused representations. Now, to manage the extent of the acoustic and visual representation that we want to capture, we used a global information fusion mechanism. This mechanism contains two gates, one for acoustic and one for visual managing. Finally, a point-wise addition is performed. Now, this whole method of fusing multimodality together, we call it as Modality Aware Fusion. Now, this whole module is a simple plug-and-play module which can be inserted into the encoder of any textual representation mechanism. For example, in this figure, we can see that we have the BART architecture with us, and we embed this whole mechanism of Modality Aware Fusion between any layer of this BART mechanism. So here we have this mechanism here inside the encoder, and we are providing it with the audio and video input, and the representation that we are getting after this Modality Aware Fusion, that is passed on to either the next encoder layer and as well as the decoder layers. These 5 architectures, namely RNN, transformer, pointer generator network, MBART and BART, give us fairly good results, with MBART and BART giving us the best and comparable results. We take both of these models forward and include multimodality information into them gradually. This table here shows the results for the same, and it can be seen clearly that the BART model with all the three modalities, that is text, audio, and video, is performing the best for the majority of the metrics. Since sarcasm explanation is a generative task, it is essential to perform human evaluation on the generated output. We do so by comparing our generated explanation on the basis of three metrics, that is coherency, related to dialogue, and related to sarcasm. We have 30 human evaluators, and based on the average of their scores, we get the following values. As can be seen from this table, our trimodal BART architecture is performing the best, though we can see that there is still a scope of improvement here. In order to validate the incorporation of various different modules in our whole architecture, we perform an ablation study. We subtract some complex modules from our system and replace them with a simpler version of those modules and get the results. Whereas in some of the ablation study, we remove a module altogether. As can be seen by this table, the best performance is still given by the trimodal BART architecture, where all the proposed modules are present. We get a Rokman score of 39%, while the burst score, which captures the semantic similarity between the generated explanation and the grounded explanation, is around 77%. Finally, here we show a qualitative instance from our test set where the trimodal BART architecture is predicting the exact same explanation that is present in the gold state. Many more such instances of qualitative evaluation are given in our paper, and all the viewers are highly encouraged to go through our paper once. Finally, coming to the conclusion, to summarize our whole problem definition, what we did was we proposed a new problem statement of sarcasm explanation in dialogues. In order to support that, we curate a new dataset called WITS. Finally, we benchmark this dataset and this problem using the Modality Aware Fusion architecture that is incorporated in the BART architecture. I have given the links to the paper and the code in this poster. You can go through them, and if you have any doubts or want to connect, we can have a chat over this email. Thank you.